All right, good morning, everyone. So I thought we would start off maybe do a couple more of these. Not actually fully analyze it, but again, just get some practice of deciding the directions of the current, applying our loop rules and our junction rules and all that stuff, just to get a couple more practice. So we'll just kind of write all those things down. And then, yeah, from there, then move on to the last topic, which is then RC circuits. Now, basically, one of these will show up on the exam. I'll tell you that now. So one of the long problems will be something like this, right? And then the problem will basically just ask you what then is the current, and then what are some other questions, and you'll see that with some group assignments. But basically, part A of the question will ask you to simply write down Kirchhoff's loop rules in the junction. And so basically, I can map then what you're doing from there. And then after that, part B then would be, we'll find the currents, in which that case you would then just use your calculator or reduce echelon form, and then go ahead and spit out the answers. In that case, just write on your calculator, or just write down using my calculator, and then give me the answers. So let's work on this one. So here I have three batteries. I have E1, E2, and E3. I have the four resistors, which again means I have, in this case, 3 loops, which means only 2 of them are going to be independent loops. And I also have 3 currents, because again, what goes from a junction to a junction has to be a current, because everything's in series. So I have a current going here, a current going here, and a current going here. So I have 3 currents. So in this case, let's choose and decide our current. So where did I go out there? I think Dalton, I think I need you don't remember? Okay, well, anyway, give me a current. Where do you want it to go? You want to go the bottom, the middle, or the top?
Let's go bottom.
Bottom, great. Which direction?
To the right.
To the right, and you want to call that I1, I2, or I3?
I1.
I1, great. So let's do that. We're going to have I1 going this way. Great. And then, well, Brooke, I think I picked on you two last time, but I'm going to pick on you again. So give me another curve. So middle or top? Top, which way? Left or right? To the right, okay. And what do you want to call that? I2 or I3? I2, great. Tim, I'll pick on you now. Which? You don't really get a choice.
Yeah, I don't get a choice. It has to go.
Exactly. Good. So we're gonna have I3 going this way. Good. Very good. So good. So now we have to choose which loops we're gonna look at. So, Ethan, what loops do you want to use? You want to use the big one and a small one, or the 2 small ones, or what do you want to do? 2 small ones. Okay. So let's look at. Let's call this loop number 1. Call this guy loop number 2. And what directions do you want to go around each one of those loops there? Clockwise on both? Okay. So for the top one, we're going to go clockwise. And then for the bottom one, we're also going to go clockwise. Good. Great. And Derek, which junction you want to use? The one on the left or the one on the right? Left. Okay, so let's use this as our junction. So let's give me my junction A. So good. So good. So again, we've done 90% of the work here, and all I have to do is apply the loop rule and the junction rule. So let's look at the loop rule first. So let's look at the first loop. So here I'm going to again start at the junction. So I'm going to go up through the battery. In this case, I'm going in the clockwise direction. So I'm going from positive terminal to negative terminal. So is that a positive or a negative? So do I get a positive increase or a negative decrease? I go from positive to negative. Or a sign rule say from history. From positive to negative, this way. It's a decrease. So we got a negative. Good. So now we're going to go through R4. R4, we're going in the same direction as the current. So if we go in the same direction as the current, is that a positive or negative? Negative, good. So I get a minus I2R4. Good. Next thing we're going to run into is then the battery. Battery, again, I'm going from positive to negative. So if we go from positive to negative, is that a positive or negative? Negative. So I get a negative E2. Then we're going to go through this resistor. So I'm going in the same direction as the currents. So if we go in the same direction, is that positive or negative? Negative. So I get an I3R2. Finally, I'm going to go through R3. Again, I'm going in the same direction as the currents, which means is that a positive or negative? So in the same direction as the current. Negative. Oh, you can't see half my stuff, can you? So I get a minus E3, I get a minus I2R4, I get a minus E2, I get a minus I3R2 minus I3R3 is equal to 0. Good. Good, so that's loop number 1. Loop number 2. So I get loop number 2. So again, I'm going to go in the clockwise direction. So I'm going to start here at A and then go through in this direction. So in this case, I'm going to start here going in this direction. First thing I'm going to come across is R3, and I'm going in the opposite direction as that of the current. So if I go in the opposite direction, is that positive or negative?
Wait, for the resistor or battery? What are we?
Resistor. So I went from here to here. Positive, good. So I get a positive, good. I3R3. Next thing I do is I come into this resistor, so I'm going in the opposite direction as the currents. So if we go in the opposite direction, is that positive or negative? Positive, good. So I get I3R2. Next thing you'll come across is the battery. I'm going to go from negative terminal to positive terminal. So is that positive or negative? Positive. So I'm going to get a positive E2. Now I'm going to swing down here and just come down through here. So in this case, I'm going to go across the resistor R1 in the opposite direction as the current I1, which means that's that positive or negative. Positive, so I'm going to get a plus I1 R1. Now I'm going to go across the battery from positive to negative. So I'm going to go from positive to negative. Is that positive or negative? Negative E1. And now I'm back at the junction. So all that's equal to 0. Finally, from the junction rule, I have what? At A, I have only I3 coming in, I1 and I2 are both leaving. So my junction rule at A simply says that I3 must be equal to I1 plus I2. That's my junction rule. So this would be part A of the problem. Let's try one more. And make it a little more fun. So let's put a resistor down here, put another resistor here, put a battery here, resistor. Good. Let's put a battery here and a resistor. So let's only do 2 batteries this time. So I get E1, E2, say R1, R2, R3, and R4. Good. Now I'm concentrating on this size because this is what we're going to see on the exam. So we're only going to see 3 loops on the exam. We're not going to see anything bigger than that. If it gets bigger, then we have more equations with more unknowns, and that's just going to be kind of. You'll see that, of course, on the homework. But as far as the exam is concerned, 3 loops is enough. Right? So again, here I have 3 loops. So again, I have 3 currents. So I have to label my 3 currents. So Tanner, give me a current. Were you going to go at the bottom, the middle, or the top?
We'll go the middle.
The middle. Okay, which way you want the current to go? You want to go to the right or to the left?
Right.
To the right, and what do you want to call it? I1, I2, or I3? I1. Great. Omar, we're back to you. So top or bottom? Top, left or right?
Left.
Left. And I2 or I3? 2. Good. And then Ruth, you actually get a choice. Which way you want it to go? Right or left?
I flip a coin.
Doesn't matter.
Right.
To the right? Cool. And of course, there are only non-choices we're going to call I3, but you could call it something else. We could call it I Ruth. What do you like better? I Ruth?
Oh yeah.
Yes. Okay. Was okay? So good, same thing as before. Now we have what? Again, 3 loops, only 2 of them are independent. So Kristen, which 2 do you want to go through? You want to go through the big one and the small ones, or 2 small ones, or what do you want?
Big one and small.
Big and a small. Okay, so let's do the big one. And which small one? The top one or bottom?
Bottom one.
Bottom. Great. And what direction do you want to go around each one?
Counterclockwise.
Counterclockwise for each? Sure. So let's do the big one counterclockwise, and let's do the small one also counterclockwise. All right. So again, for loop 1, we're going to start off at some point. Oh, we need a junction. So Jessica, which junction do you want to do?
To the right.
The right one this time, just change it up. Okay. Let's call that junction. So good. So let's do the bottom, or actually the big one first. So again, wherever you want to start, it doesn't matter. I'm going to start at the junction just because it's a nice reference point that I have on here. So I'm going to go in this direction. So again, I'm going to come up through here. I'm going to go through first R4. R4 going in the same direction as current I2. So if I go in the same direction, is that positive or negative? Negative. So I get a minus I2 R4. Next thing I'm going to go across is the battery. I'm going to go from the negative terminal to the positive terminal. If I go from negative to positive, is that positive or negative? Positive. Good. So I'm going to get a plus E2. I'm going to ride this guy down through here because I'm doing the big one. So I'm going to go through the junction down through here. First thing I run into now is R1. R1 I'm going to go through in the same direction as I root. So is that positive or negative? Negative. I get a minus I root. R1. Finally, I'm going to go through R2. R2, I'm going to go through R2 in the same direction as I root. So is that positive or negative? Negative. So I'm going to get a minus I root. R2. And I'm back at the junction, so all that has to be equal to 0. Okay. Loop 2. Here, again, we're going to go in this direction around this loop. So I'm going to start here at junction A and go through in this direction. So first thing I'm going to do is come across the battery E1. E1, I'm going to go from positive terminal to negative terminal. So is that a positive or a negative? Negative. So I'm going to get a negative E1. Now I'm going to go across resistor R3 in the opposite direction as I1. So is that positive or negative? Positive. So I'm going to get a plus I1 R3. Now I'm going to swing down here through this junction, come through here. So in this case, I'm going to go through R1 in the same direction as I root. So if I go in the same direction, is that positive or negative? Negative. I get a minus I root. R1. And then again through R2 in the same direction as I root. So again, is that positive or negative? Negative, I root. R2. And now I'm back at the junction. So all this then again has to be equal to 0. At the junction, what do I have coming in? I have I1 coming in, I root coming in, and I have I2 leaving. So for my junction rule, we then have to have that I root plus I1 must be equal to I2. So what's coming in must be equal to what's going in. That's it. Over and over and over and over and over. So again, the way that we choose these things doesn't matter. We can choose the currents to go in any direction. Here, the currents were chosen to go in the direction in which the battery would force them to go. So again, that's a natural choice that we can take, but that won't always be the case. But again, from there, all we're doing is deciding which loops to go through, what directions that we're going to go through, use our sign conventions, and life is great. So the nice thing about this is there's minimal thinking. Actually, almost no thinking. The only thing you have to do is be consistent with what it is that you chose. That's it. Unlike an engineer where you guys do the mesh analysis where you can say this is positive, this is negative, blah, 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 blah. All that stuff is gone. All I care about is how I decide to go through the circuit. That's all I care about. There's no thinking that's involved. Okay? So our last topic then, we're going to start talking about something we saw in class, which is what's known as an RC circuit. Actually, not in class, but in lab. RC circuits. So what's an RC circuit? So an RC circuit is literally a circuit which is created by a resistor, hence R, and a capacitor, hence C. So these are circuits that consist of a resistor, R, and a capacitor, C. So great. Now, we're going to be interested mostly in two different scenarios. The two different scenarios we're going to be interested in is a charging RC circuit and a discharging RC circuit. So let's start off with a charging RC circuit. Let's talk about how this is going to work. So for a charging one, we're going to take a battery. We're then going to connect that in series to a resistor, which is then connected in series to a capacitor. Now here, I'm going to look at only when these guys are connected in series, not when these guys are connected in parallel, because that'll be a whole different analysis. So let's just look at this one for now. So let's say initially at t is equal to 0, the charge on the capacitor is equal to 0. So let's say that this thing starts off with an initial charge which is equal to 0, and then what's going to happen? So what's going to happen, as we talked about when we talked about capacitors, is I'm going to take a positive charge from here, run that then through my system, which means I'm going to create a current, and then that positive charge is going to end up being deposited onto this plate, which is then going to kick off a positive charge on this side, moving it then in this direction so that this thing ends up with an overall positive charge. This one ends up with an overall negative charge of the same amount. Then I'm going to try to put another positive charge, draw that in gray, dump that onto here, but now I have a coulombic repulsion that I have to overcome to put this positive charge on top of this one, which simultaneously would kick off a positive charge from here, again, leaving this guy with then 2 positive charges, this one with then 2 negative charges. Now, every time I try to dump another charge on top of this, my battery then has to do more and more work to overcome that coulombic repulsion to then put a charge on here. So what's going to happen then is that this system is going to run initially very easily. Because again, to move one charge onto here, there's no pre-existing charge on here, which means there's no potential, which means it's very easy for me to put on there. I have to do no work. Which means that initially, the charge is going to start to grow on top of this plate very, very rapidly, almost linearly. But as more and more charge starts getting on top of here, what's going to happen? The rate at which the charges are going to be put on top of here is going to slow down because it's going to take more and more amount of work to start putting more and more charges on there, which means that my plot then is going to start to flatten out. Until eventually, what's going to happen then is I'm going to reach the maximum amount of charge that I can put on top of the capacitor based off of the potential difference of the battery. Which means that this thing is going to asymptote till it reaches the actual maximum amount of charge I can actually put onto the capacitor. So what that means then is what? If I plotted, for example, the charge versus the time, initially this thing is going to grow very, very rapidly. It's going to do something like this. But as time goes on, this thing is going to reach the maximum amount of charge that this thing can put, which means my plot is actually going to turn around and then start to asymptote and then do something like this. Right? Until eventually I'm going to reach then my maximum amount of charge. So again, initially, this thing is going to move very, very rapidly. It's going to go almost linear, and then it's going to start to taper off. In this case, slowing down as I'm trying to put more and more charge on there until eventually it asymptotes to the maximum amount of charge I put on. Now, when I think about the currents, what happens with the currents is as soon as I initially set this thing up, current will be flowing maximally because I have no charge on here. I have no coulombic repulsion trying to push the charge back, which means all the current is going to be based off of simply that of the resistor. Which means that the current initially will simply be equal to, by Ohm's law, the potential divided by the resistance. But as I start getting more and more charge onto here, the rate at which the charge is going to be deposited is going to slow down, which means the rate at which the charge will be flowing through the system will slow down, which means the current will getting smaller, until eventually what's going to happen is once this thing asymptotes to the maximum amount of charge, the current will go to 0. I will no longer be able to run a current throughout my system. So what's going to happen here then is at this time, even though the charge is equal to 0, the current will be equal to a maximum. Now, as time goes on, so as t goes to infinity, what will happen then is that Q will become equal to Q max, while the current will go to 0. So this means what? If I plotted the current versus the time, this thing is going to start off at whatever the maximum current is. So this is I max, but we know by Ohm's law, I max is simply going to be equal to this way, E over R, right, from Ohm's law. So it's going to be the EMF divided by then the resistance. And if I plot this thing is going to do something like this. This is what the current is going to do. So the current is going to start off at its maximum, but then slowly go to 0, actually rather rapidly, actually exponentially go to 0, only going to 0 when it reaches maximum charge, which technically happens at infinity. So what we want to know then is what is the time dependence then of the current, and what is the time dependence of the charge? So how does this thing actually depend on time? And then how does the current actually depend on time? And the way we're going to do that is by using Kirchhoff's blueprints. So let's analyze this circuit here. So I have this is my scenario. So this is my positive, negative, my resistance, my capacitor. So what's going to happen is this is the positive side. This one is going to become positively charged. This side then is going to become negatively charged. Now from here, I want to use Kirchhoff's loop rule. I have no junctions here, so I don't have to worry about the junction rule. But I want to start here at this point and then analyze the circuit as I go around to this point. So this is going to be my starting point down here. We're going to go through my circuit in this direction. So Kirchhoff's loop rule says that as I go through here and I transfer the battery, I'm going from the negative terminal to the positive terminal, which means I get a positive increase in potential. So my Kirchhoff's loop rule says that I get an E. Now I'm going to go through the resistor in the same direction as the current, because I know my current is going to be moving through in this direction. So in this case, I'm going to get a minus I times R. And then we're going to go across the capacitor from the positive terminal to the negative terminal. And as we wrote down yesterday, that then manifests itself as a negative drop of potential, which is then Q divided by the capacitance. In this case, I now come back to the junction over the point I started off, so the change in potential has to be equal to 0 by my loop rule. Everyone's okay with this? Now, however, what we know is that current, by its definition, is equal to the change in charge divided by the change in time. Which means I can rewrite this thing then as E minus R times dq dt plus, or sorry, minus Q over C then is equal to 0. So what happens then is I've gone from an algebraic expression, which is this guy, by realizing that this thing is actually the derivative of the charge, to now it's known as a first order differential equation, or something that we've seen before. This thing is now a derivative, which means to find the charge, we're going to have to do an integral. Okay with this? Sounds good. So now what? So now what I'm going to do is I'm going to subtract this guy then over to here. So let's do that. So in this case, I'm going to get an E minus then Q over C is then equal to R dq dt. Next thing I'm going to do is I'm going to factor out 1 over C. So I'm going to get 1 over C then is E times C minus Q is then equal to R times dq divided by dt. So now what I'm going to do is I'm going to now divide this R over here, divide this term over here to get all the charges on one side, and then bring the dt to the other side. So I'm going to do what's known as separation of variables. You've seen this 1,000 times in class, but this is just what it's actually physically called. So let's do that. So basically what I'm going to do is I'm going to bring this R down here. I'm going to bring this term over to this side, and I'm going to bring the dt to this side. So what I want is all the Q's on one side, anything that's not a Q on the other side. So let's do that at the same time. So this is going to be then equal to dt divided by RC. Then it's going to be equal then to dq divided by E times C minus Q. Now from here, I'm going to integrate both sides because what I want is the charge, not the differential charge. So let's now integrate both sides. I'm going to integrate this thing then from 0 to t, and integrate this guy now from 0 to the maximum amount of charge. For the left-hand side, RC is simply a constant. So I'm going to pull that side of the integral. So I'm going to get an integral of dt. Well, what's the integral of dt? T, evaluated from 0 to t. So the left-hand side is simply going to be t over RC. That's my left-hand side. What's the right-hand side? Well, the right-hand side, I'm going to use a U substitution. Okay? So in this case, what I'm going to say then is that, well, U is equal to, U is equal to EC minus Q, which means DU then is going to be equal to a negative of DQ. You okay with that? And E and C are both constants, so I can't take a derivative of them. So the only thing I take a derivative of is this. on. Sehr gut. Or not for German. So now let's plug all that back. So this thing now says that I have what? T over RC is then equal to the integral negative du over u. But now I need to change my bounds of integration. Right? So here, to change my bounds of integration, I'm simply going to look at this guy here for when first q is equal to 0, and then when q is equal to q. So when q is equal to 0, that tells me u then is simply equal to c e times c. And then this is then u then is equal to e times c minus q. So my bounds of integration then are going to be from ce minus then ce minus q. Okay? Well, last thing I'm going to do is I'm going to move the negative side to the other side. Just for see why we get there in a second. Great. What's the integral of du over u? Natural log, good. So it's going to be the same thing then as the natural log of u evaluated from u is equal to c times e to u is equal to c times e minus q. So it's going to be the same thing then as the natural log of c times e minus q divided by c times e. Now again, what I actually want is q. I want to know how much charge is on my capacitor as a function of time, and then from there we're going to get to current. Okay? Remembering that the current again is a time derivative of the charge. How do I get rid of a natural log? What is the inverse mathematical operation of a natural log? E. So let's exponentiate both sides. So now I'm going to get an e to the negative t over rc, then is equal to simply c times e minus q divided by c times e. We're almost there. Now, again, what I want is q, so I'm going to multiply both sides by ce, and then I'm going to subtract this term over to here, and then add the q to the other side. So let's do the two things simultaneously. So what I'm finally going to get then is that q is equal to what? Ce minus ce times e to the negative t over rc. But they both have a CE, so I'm going to factor out the CE, so it's going to be then equal to C times E times 1 minus E to the minus T divided by RC. So this is my charge on the capacitor as a function of time. Now, what does this thing say? What this thing says then is, again, at T is equal to 0, anything raised to the 0th power is what? 1, so this is going to be 1 minus 1, which is simply equal to 0, which means that time is equal to 0, I have 0 charge, which is exactly what we said is happening here. So at time is equal to 0, we have 0 amount of charge. As time goes to infinity, what happens? Well, as time goes to infinity, I have an e raised to the negative infinity, which is the same thing as 1 over e to the infinity, but what's e to the infinity? Infinity, so I have a 1 over infinity, and what's 1 over infinity? 0. So as t goes to infinity, this term goes to 0, which then leaves my charge simply equal to the maximum charge, which is the charge which is based off the capacitor, which is c times the potential. This matches perfectly with what it is we said should happen. If I actually plot it out, what I find is that this plot actually does completely match this plot here. So this is the actual time dependence of how this variable plate capacitor charges over time. So this guy. So again, what this thing says then again is at t is equal to 0, we have e to the 0 is equal to 1. So in this case, my charge on the capacitor is equal to 0. T goes to infinity, we have e to the negative infinity, which is equal to 0. In that case, we have QC is equal to Q max, which is equal to C times E, which we know has to be true because we know that charge is equal to capacitance times potential. So in this case, all the potential is going to be across the capacitor with 0 potential across the resistor because there'll be no current flowing. What about the current? So let's look at the current. Well, we know the current is equal to the time rate of change of the charge. So in this case, it's going to be equal then to the time rate of change of then c times e times 1 minus e to the negative t divided by RC. In this case, this is the constant, so come outside of the integral. Here, this is a constant, so this is going to go to 0. And then I end up with the derivative of the exponential. Well, what's the derivative of an exponential? An exponential times the derivative of the argument. Right? So the derivative of the argument in this case is simply going to be negative 1 over RC. So that negative is going to cancel this negative. So this guy is going to be equal then to what? C times e to the t over RC, all times 1 over RC. But the c's are going to cancel, which means my current then is going to be E over R times e to the negative t over RC. What does this thing say? Well, this thing again says that at t is equal to 0, my current then is equal to the maximum current, which is simply equal to E over R, which is what we said it should be. As time goes to infinity, in this case, the current is simply going to be equal to 0 because again, the exponential will be equal to 0. So again, our current will go to 0. This is exactly what we saw in lab. Now, the rate at which this thing does it is dependent on this quantity here. This is what's known as the time constant. So another way that I could rewrite each one of these is I could say, well, the charge on a capacitor is equal to C times E times 1 minus E to the negative t over tau. And I can write the current then on the resistor is then equal to E over R, E to the negative t divided by tau, where tau is equal to what's called RC. So this is what we call the time constant. So what controls the rate at which the exponential goes to 0, or the rate at which the charge actually increases, is all dependent on both the resistance and the capacitance. This is what controls the rate. What does the time constant mean? So time constant means that when the time is equal to the time constant, tau, then the current then is going to be equal to the maximum current times e to the negative 1, which is the same thing as I max divided by e. So the time constant then tells me is how quickly does this thing go to 67% of the rate. So this is what the time constant says. So the smaller the time constant, the faster it is that it gets to 67%. Which again is what you saw in lab, because with the round bulb, that had a small resistance to it, which means it had a small time constant. With the long bulb, that had a larger resistance, which means it had a longer time constant, which means it took more time for that thing to charge up, because it wasn't moving as quickly because the time constant was bigger. Okay? So what dictates the rate at which this thing is going to go is both the capacitance and the resistance. This is what dictates the rate at which this thing is going to either be charged or discharged. Now for discharging, we basically have the same thing. I'm not going to analyze it. I'm just going to tell you the results. So what happens for discharging? So in this case, we're going to take a full-blown capacitor, which starts off with a maximum amount of charge, Q max, or an initial charge, let's call that Q initial. And we're going to hook it up directly to a resistor, and I'm only going to make this guy myself. Okay. So again, this is how you guys discharge your capacitors in lab. In this case, if I think about the charge, what happens in this case is my charge starts off initially at its initial charge, Q initial. As time progresses, what we saw in that case then is this simply exponentially done into this. The current started off again at maximum. So I start off at maximum or my initial amount of current. As time went off, this thing also simply died. Also exponentially quickly. So in this case, what you find is that the charge on the capacitance is equal to the initial charge times e to the minus t divided by tau. Then you find the current across the resistor is then equal to the initial or the maximum amount of current times e to the minus t divided by tau. So they both exponentially decrease. Where tau, just like before, is dictated by the resistance and the capacitance. So these are what we call RC circuits. So RC circuits are kind of interesting circuits. RC circuits are actually used by you every day. Assuming certain things. For example, when you drive your car, if you actually use your signal, which in Evansville is not a given. But what's a signal? It's an RC circuit. What tells your light to flash, in this case, is you're actually charging a capacitor. When it reaches then the maximum charge, that charge is enough to then have equal the breakdown potential of the gas, which is basically on the inside of your light bulb, which then basically causes it to flash, discharging the gas, and then you recharge it. Your windshield wipers are an RC circuit. When you're driving down the road and you see construction work and there's flashing lights, that's an RC circuit. A pacemaker is an RC circuit. So all of these different things, anything that rhythmically flashes based off of a different time are all simply RC circuits, where each one of the times are dictated by simply the resistance. So again, if you want a quick windshield wiper, then you have a very small resistance. If you want a slow windshield wiper, then you have a very large resistance. So all of these things are based off of simply RC circuits. So anything that flashes regularly, again, your signals, your pacemakers, your windshield wipers, all of these things are simply RC circuits. So, what's up, Tim?
Do these equations still work as R goes to 0?
As R goes to 0?
So as you keep getting less and less resistance in that circuit.
To a particular point, yes, but not when R goes to 0.
Which, I mean, it's just in theory, because you're never going to have 0 resistance.
Well, that's not technically true. Those are called superconductors. So technically in a superconductor, this would not. But yes, anything that's not a superconductor, then the answer to that would be yes. So no matter how small the resistance is, now what would happen though is that if you had a ridiculously small resistance, the frequency at which it would do that would be so quick that we wouldn't really see it flashing. And so what we would see is a constant light. We wouldn't see the pulses that are basically happening because the frequency would be too great. So as things are oscillating so fast, we don't really notice its maximum. We also don't notice the minimum. We notice what's known as the RMS value. So we'll talk about that when we get to lights. So the light that's coming to us is actually oscillating all the time, but we don't see the oscillation because the frequency of the oscillation is so great that we see its RMS value. We can't really notice it. Same thing with the power that comes out of your house. Right? So this is actually AC circuit. So the current is actually constantly changing direction and doing things. But again, you don't notice that because the frequency is so high that what you notice again is that RMS value. So yeah, so in theory, it doesn't really matter. So this would go almost all the way down to 0. But again, for a regular type of conductor, which is what Ohm's law satisfies anyways, then you could never actually get this. But yes. But if you go to a superconductor, then yeah, this doesn't work. Okay? All right, so let's do a couple examples of this, and let's see how all this actually works. There we go. Got those over there. So it says take the capacitance in the circuit below here as 0.3 microfarads and the resistance as 20 kilo ohms. And a battery here has an EMF of 20 volts. And then it wants us to determine the time constant. So tau, the maximum amount of charge the capacitor could have, the time it takes for the charge to reach 99% of that value, assuming that it starts off at 0, and then the maximum amount of currents. So those are what we wanted. So let's label all these things. Example. So we have the capacitance was equal to 0.3 microfarads. We have the resistance was equal to 20 kilo ohms. Then we have the EMF was equal to 12 volts. And then from here, we want to know as part A, what's the time constant? So we now know the time constant is simply equal to R times C. So we know this is going to be the resistance times the capacitance. So this is going to be 20 kilo ohms. So it's 20 times 10 to the third ohms times then 0.3 times 10 to the minus 6 farads. So this works out to be about 6 milliseconds. So 6 times 10 to the minus 3 seconds. Put it that way. So this is my time constant. Good. Part B, we now want to know what is the maximum charge. We know the maximum charge is simply going to be equal to C times E, because again, based off of our charging expression, the maximum charge occurs when, again, this thing is equal to 0. As we wrote down, the maximum then is going to be simply the capacitance times the potential. So here, our maximum charge then, expression is C times E, so this is going to be again 0.3 microfarads times then 12 volts. So it's going to be 36. 3.6 microcoulombs. So that's my maximum charge. What's up?
Does the circuit itself even math?
I'm sorry?
Does the circuit itself even math? Like they provided a circuit. Do we need to analyze?
Oh, in this case, yes and no.
Like, what would we do
So
with
the answer to this is, as long as we see that this is connected in series, then anything we just did works.
okay.
But if it's connected in parallel, then no. Now we'd have to actually go through all of this stuff to then rederive all of those equations. Does that make sense? Because now these things won't act exactly the same way. So yeah, so if, for example, if this problem said we actually had something like this, so if I had, say, the battery here, and then this guy was connected to the, let's do it this way. If I said the capacitance was here, and then the resistor was here, so these guys were actually in parallel, not series, then you would actually have to re-go through all of that to now rederive what the time constant is, as well as all the other good stuff. So in this case, you'd have to worry about, again, to do that, you would just use Kirchhoff's loop rules again. So you would look at this loop here, look at this loop here, and then you'd have two different currents. So you'd have a current running through here and then a current running through here, and then you basically have to go through and rederive all those things based on what that stuff. Not to sound like a dick, I haven't done this in a long time, but the first time I taught this class, I gave something similar, where there were things that were in parallel and series, and I made them go through and figure out the new time constants and all that stuff. Just say I had higher expectations than that, so I haven't done that since. Needless to say, it didn't go that well. Everything's okay? Too bad. So let's go to part C. So part C then says, okay, how much time does it take for this thing to reach a charge, which is then equal to 99% or 0.99 times the maximum charge. So in this case, we know what the final charge is. What we want to know then is what is the time that it takes to do that. So what we know is that what Q is equal to C times E times 1 minus E to the minus T divided by tau. But we know CE is simply equal to the maximum charge. So we get Q max then times 1 minus E to the minus T divided by tau. Now in this case, when we know that Q has to be 0.99 times Q max, then be 0.99 times Q max is then equal to Q max times 1 minus E to the negative T divided by tau. Now here, this Q max, of course, we can just cancel this Q max. I don't really actually care what Q max is. So now I can rewrite this as 0.99 is then equal to 1 minus E to the negative T divided by 10. What's up, President?
How'd you get that 0.99 on the left side?
Oh, so it told us in the problem that we wanted when it was 99% of the maximum amount of charge. So in this case, we're simply saying that we want Q
To equal 0.99.
exactly, because 99% is 0.99. Good. Good. So in this case, what we want is the time. So we're going to isolate the time. So we move the exponential to this side and subtract this on to this side. So it's going to give me an E to the minus T divided by tau is then equal to 0.01. Now here, however it is that I want to think about doing it, but I want to get rid of that negative sign, so I'm actually going to invert both of these two. So for negative sign, this is actually 1 over e to the negative t over tau. So I'm going to invert both of these. So that's going to give me e to the t over tau is then equal to 1 over 0.01, which is the same thing as I. Now again, what I want is t, so how do I get rid of an exponential? Natural log, so let's take a natural log of all times. So here I get a t over tau then is equal to the natural log of 100, which means then that's what t is equal to tau, which is my time constant, times the natural log of 100. So this is the amount of time it's going to take for this thing to reach 99% of its maximum charge. Look at my numbers. What I find in this case is this works out to be 28 milliseconds. So in this case, it only takes 28 milliseconds for this thing to reach 99% of its maximum charge. Now, technically, for this thing to reach 100% of its charge, it would take an infinite amount of time. But if I was watching this, I couldn't tell the difference between 99% and 100% just by watching it, because again, the battery's going to be, there's not going to be any light from the light bulb. So as it moves up to 99.9%, it takes more time and then more time and more time. So the time gets extended from there. But I guess technically for this thing to reach 100% of the charge, it would take an infinite amount of time for that to actually do that. What was the last thing we want to know? The maximum current. So part D, we want to know what is I max. So I max we know is simply going to be E over R. We know maximum current is simply going to be dictated by the battery and the resistance. So it's going to be our 12 volts divided by our 20 kilo ohms. So if I divide those, what I get in this case then is I max is 600 microamps. So it's my maximum amount of current I have flowing through the system. I have another short one here. This is a really short one. So this has a typical turn signal flashes twice a second, so that the time constant is 0.5 seconds. The RC circuit controlling this may have a capacitance of 1 microfarad. What then is the resistance of the resistor? So this is about as straightforward as possible. So for this one, again, we know our time constant is simply R times C, which means we know tau, we know C. That means our resistance then is just going to be the time constant divided by the capacitance. So we know our time constant was 0.5 seconds. We know our capacitance was 1 microfarad. So this is 1 times 10 to the minus 6 farads. Again, plug in our numbers. This works out to be about 500 kilo ohms. So this is our resistance in that resistance. So good. So this is RC circuit. So we are officially done with all the material. Okay, so tomorrow I have 2 group assignments for you. They're actually already posted on Blackboard. I did that this morning, but we don't have time to do it today, so we'll talk about them tomorrow. So we'll do a review tomorrow. We'll talk about those group assignments. I'll let you work on those, and then whatever other group assignments that you have, and then ask whatever questions that you guys want tomorrow. So that's officially what we'll do tomorrow. Tomorrow we're not going to learn any new stuff. I'm just going to do the group assignments and what's up, Richard?
I got a question on that question.
Sure.
What was that rule that you used with the negative on that one?
Oh, so all I did was here. So what I said is that this is the same thing as 1 over e to the t over tau because of that negative. So basically what I want is I'm just going to invert both of these to then get the negative sign involved.
Yeah.
So it's basically what I'm doing. The other way you could have done it is you would have left that negative sign. So here, what you could have done then is you would have a natural log of negative t over tau is equal to natural log of 0.01. And then from here, that would give you a negative t over tau, which would equal to the natural log of 0.01, which means the time then would be negative, the time constant, natural log of 0.01, which will give you the same answer, because anything that's below 1 has a negative natural log. Okay. So in that case, your natural log would be negative, that negative would cancel. So whichever way you want to do it, but it's up to you. What's up?
Where did this fit?
Oh, so that was just saying, so I was trying to give you a physical idea of what this was, but all I'm doing is I'm using that into this expression. So I'm saying, well, it's easy with the tau, this term is simply gonna be I max, the overhard is I max, so this is simply gonna be e to the negative. And then I'm just putting the e at the bottom. So basically, all it means is that, again, according to this, that you reach about 67% of the maximum current in that case.
Okay.
So that's what the time constant is telling you. So it's telling you the rate at which it takes for this thing to reach 66% of its maximum.
And I know that like. For this, we set it up like this. So if it was a parallel, you'd actually have two systems of equations because you have the one loop and the one junction.
Correct.
And then you just solve it for.
That's right. So in that case, let's go to there. So we'll talk about that one. Yeah, so in that case, then if I have the battery here, let's connect the capacitor here, resistance here.
Yeah.
That's right. So I would use the junction. And then, so this is again, 3-loop system. Right? So I have one loop here, and then 3 loops.
Yeah, so you use 3 equations.
Exactly.
2 for the either loops and 1 for the.
Exactly. So basically, I would call this, I don't know, say I1. From here, I'd have a current going through here. Let's call that I2, and then from here, I'd have a current going through I3.
Yes.
Exactly.
And you do the exact same thing except just
Exactly.
replace the capacitor with Q or
You would replace the currents with the time rate of change. Yeah,
yes.
that's right. So in this case, then you would get a I2 plus I3, right? You would. And then from here, you would have your 2 loops. So I would end up with E minus Q over C is equal to 0 from the first loop. And then
Yes.
from the second loop, they're in opposite directions. So in this case, I'm going to get Q over C minus I3R is then equal to
Yeah.
0.
So you just use Q or C for any capacity.
Correct. Yes. Yeah.
What's the sign? Do we learn the sign convention for capacitor?
Yeah. We did that. It's in here somewhere.
We just haven't done a problem.
We just didn't do a problem until today.
Yeah.
Yes. That's right.
Well, technically, that's like really.
Not really a problem as far as this is where it actually
But,
comes from.
yeah, that could be very easy though.
Oh yeah.
Yeah.
Yeah. I mean, it'll take a couple minutes to kind of do it. But
Yeah, and then after that, you have to
So then you would have to recombine everything together to then find, yeah, so what is the overall charge on the capacitor? Just basically do all the same stuff.
yeah, you basically separate the DQ and the DQ.
Exactly. So separate all those variables and do all the same things. Yeah.
And you try to. I guess my question is, well, when you're entering this stuff, you would not be entering this stuff in the
No, in this case, no, because you'd be solving an integral in this case. So this would not be an integral.
So
Yeah.
how would you combine the 2 equations?
Oh, so let's see here. So basically what's going to happen is the current which comes out of the battery is only going to be dictated by this guy, but that's going to be time dependent, right? So basically what's going to be happening is all of these currents will be time dependent. So you'll have to kind of put those together, rewriting that current through each one of those is basically dq over dt.
So you would integrate all of them?
Well, you combine them together to get one expression that you would.
Oh, so you can actually do a thing where you like add.
Exactly.
Okay. I
Exactly.
remember learning that very back in the day. Combine them. I think you also forgot your, no, they have a junction.
I have a junction equation. That's the first thing you wrote in. Yeah.
Yeah.
Okay. What's up, Paige?
I just have a quick question.
Sure.
So when we did the example here,
Yep.
I know that Q max equals C, so we replaced it here.
Yep.
Why did we set it to the 0.99?
Oh, because we were looking specifically for the time where this charge on the left-hand side, Q, was equal to 99% of its maximum charge.
Okay,
So that was dictated by the problem. So the problem was to find the time it took for this charge here to equal 99% of the maximum charge.
so did it just kind of tell us to set it to that? basically?
Well, it's implying that when it says that it wants to know the time so to get 2.99%.
Okay, because there was no formula that like said that Q equals T, right?
No,
Okay.
yeah, but that left-hand side is just the charge at a given time.
Okay.
So that's what, let me turn this on.